So before I start, I want to thank my colleagues, my student Shivam, who did all of this work, and my collaborators Iran and Tommy Pocho from MIT. So basically the talk today, I want to kind of challenge a few ideas and concepts in machine learning. So basically, what kind of questions can we solve with machine learning, and what type of algorithms should we use in machine learning? So before I start, I kind of want to start with the very basic question: what is machine learning? So basically, at the heart of machine learning, we have almost always something that looks like this, right? We have some training data set. In this case, it's supervised data, so we have labeled images. And then basically what we're trying to do is to learn the mapping from X to Y, right? There is some function here, Y of X, that maps images to labels. Okay, so let's say we have data of cats and dogs and we want to classify them. And the process that we do that is by introducing these two components. So we have some learning algorithm, and it has access to a hypothesis space. So let's say like in our network, parameterized with some weights. And then we want the learning algorithm to come up with a function from this space that matches the data. Okay.
So you need these two and the others.
What's that?
You need the architecture before you can start doing gradient descent. No?
I was thinking about different ways to organize it, but I agree with you. There's another way of thinking about it. But yeah, so another way is like this. My thinking is you have the data, the learning algorithm produces a model. Anyway, so we try to feed the training data, but the actual goal is to perform well at test time, right? So we have some held out data, and what we care about is the performance on that set. Okay. So basically, the idea of machine learning is to try to design algorithms that learn well. And in the sense that the goal is to basically design these two components such that we need as few samples as possible. Or on the flip side, if we have a fixed data set of a certain size, we want to make the best of it, right? So that's the idea, like sample efficiency, how to take advantage of a given set of samples as much as possible. And like the vast majority of research traditionally, like in deep learning and machine learning, has been designed to kind of like think about these two components. How should we come up with a good model, a good architecture, and a good learning algorithm? Okay, so 95% of deep learning research has been devoted for these two things. So what are some classic machine learning tasks that we have? So this has been very rewarding, right? Like this process, we're able to do image classification, medical diagnostics. We can do in natural language processing. We have sentiment analysis, spam detection, speech recognition, and emotional recognition, and all of these applications, right? It's a very powerful tool that can be applied for so many things, right? But in some sense, we kind of channeled ourselves in our research to these specific questions, right? We realized that these tools are very good for things like computer vision tasks, so that became our world, right? We focused on machine learning for vision or for NLP or for audio, all of these things, right? And now in the era of LLMs, we kind of are challenged with new types of questions, right? Of reasoning and math and manipulating symbols and arithmetic and all of these things. And that kind of introduces certain problems that are not obvious when it comes to like traditional machine learning tools, right? So for example, we could kind of, ask if this framework applies to these type of questions. Okay, so let's say questions in number theory, right? Like classifying numbers if they're primes or not, okay? Or in graph theory, is it like a connected graph or not connected graph? It's also a classification problem, right? But not of cats versus dogs, right?
And do you mean here really pure LLM, or do you allow it to use tools?
So like as a learning problem, so you are provided with data of, let's say, 100-digit numbers of like primes and non-primes, let's say half are prime, half are non-prime, and you want to learn the pattern. So you want to come up with a model that is able to tell apart between these two groups.
But a model that's doing next token prediction, not a model that's allowed to learn how to write a Python code, run the Python code and report the answer.
So actually the latter.
Okay.
Yeah. So not to do like next token prediction or something like that. Yeah. The next token is the label. You just want to predict the label. Yeah. So we could like encode graphs. Oh, so, yeah.
Sorry, I don't, so if the LLM can do tool calls, then it can just run a Python code to check whether the integer is prime by saying, testing every possible divisor. So you're saying the LLM can do tool calls?
Yeah, so let's say like you just give, so basically the setting is that you have a data set of some vectors, let's say binary vectors, okay? And you want to learn like why one group is 0 and one group is 1. So you don't know like what is the real function behind it that classifies between the two, and you want to learn this function. Okay, so let's say you have some property in graph theory, and you want to learn that property. So to come up with some function that will be able to classify if it's within the property or not. Okay. So yeah, of course, like if you know that it's primality, then you can tell the LLM like just write the code, right? But you don't know that it's primality. So like here, it's an example that we're all familiar with. But what if you're provided with some arbitrary property? Yeah.
There's like fun search.
Hmm?
Talking about fun search.
What do you mean?
Fun search, this DeepMind, they're trying to find a function that they're trying to write a function that produce this. Anyway, let me
I'm not
keep going.
familiar. Yeah. Yep.
I think it's in the same direction that, so it's the question that they're learning without prejudice or learning with prejudice. So like if, if it has for the internet and so it understands that, okay, it could be any kind of division, but humans like primes and non-primes. And so then it says, okay, so it looks like prime, so let's write the program. But it says looks like primes because there is all this knowledge that it acquired on the internet.
Right.
So it's like with prejudice, I would call it like that, like the human with respect to the entire human culture, and that's different. Yeah. Okay. So you understand the point.
Yes. Yeah. Yeah. So basically, all of these questions are kind of like not obvious for traditional learning algorithms, right? Like it's not like we can apply a convolutional network on numbers and expect it to learn well, like if something is prime or not, right? So that is kind of like what I want to focus today. Okay, so let's say we have labeled primes and non-primes. That's my training data. So let's say 100-digit numbers. Okay, so really big numbers. And then I want to kind of like design a learning algorithm and the space of functions from which I choose my function to be able to solve this type of tasks. So all of the types of tasks that I described earlier. Okay. So the example that I want to use for kind of like start with and also do some analysis from a theoretical standpoint is the parity function. Okay, so the parity function is very amenable to analysis, so it's pretty useful. So like a k-parity function, I guess most of you know, is basically a function over, let's say, 100 binary digits, and it has some subset of k variables, and then it computes the XOR of these variables. Okay, so let's say we have 4 variables. This is a 2-parity function that takes XOR of x1 and x3. Okay. And then come the question, okay, let's say we have training data from this function. So we're basically provided with random vectors, binary vectors, and some and the labels. Okay, so basically the output of the k-parity function. How can we learn that function? Okay, from the data. And the first option, the most naive approach, is to try to use what we're most familiar with, right? Like doing deep learning, doing modern machine learning. So basically, deep learning has three main components, right? So we have the model, let's say a transformer that is not trained yet. Okay, so this architecture. We have some loss function that we introduce to measure the error. And then we have the optimizer, let's say stochastic gradient descent or the Adam optimizer, some gradient-based optimization technique. Okay, so we summarize the error as a loss function, and then we try to optimize the parameters of the model to fit the training data. Okay, so that's option number one. And we tried that on the parity function. So let's say we have 10 parity function on some inputs of different dimensions. So in each experiment here, we basically ran training some transformer with 75 million parameters for a long time. And we wanted it to fit the data of a 10 parity function, a random 10 parity function. And we wanted to kind of like see how it performs, okay? So what we see is that basically it perfectly fits the training data, but it completely overfits. So learning the parity function, this is kind of like a well-known thing, is very difficult with this approach, with classic deep learning, like training from scratch, a model with stochastic gradient descent. We see that it doesn't work. Okay.
It's a fairly small model that they're using.
Yeah,
Okay.
I agree. We tried many different types of models, like
Still.
nothing works. Yeah, like you take bigger models, you take smaller models. Just note it completely fits the training data, 100K samples. You don't see any progress, right? And basically that kind of led us to the belief that we need to challenge this idea of deep learning. We need maybe like to think about new machine learning algorithms for this type of problems. Okay, so the reason why we fell for deep learning is because we got these impressive results on computer vision and speech and language and all of that. So we have this big hammer, but not everything is a nail. So for example, the learning of k-parity functions is not necessarily a nail that is suitable for this hammer.
On search work on,
What's that?
I haven't tried this before.
Sorry?
are you gonna talk about fun search or,
I'm not familiar with that.
they're another name for it, like, they changed the name recently, you know, it is, just for 10 seconds, it's a Google, DeepMind thing where they have LLMs write 100 different programs,
Mhm.
just completely randomly, just write programs that do things. They test the programs on the data. The ones that do well, they keep, you know, they keep the top 4, and they just tell an LLM, write 20 more programs like these top 4. And then they just iterate that again and again and again. They try by evolution to
Yeah,
find a program that performs well on it. That's another kind of big hammer
Mhm.
that uses, you know, I mean, LLMs and deep learning, but in a slightly different paradigm that tries to find solutions to problems like this. I don't know if it's been tried on this problem, but whether it's used there.
So I'm not familiar with that work, so I don't want to, you know, say something that is wrong. But I'm happy, you know, to talk about it and look into it more.
I just remember that the new name is Alpha Evolve.
Alpha evolve, Aleph evolve,
Alpha Evolve.
Aleph evolve, like Aleph 0, Aleph,
So
Aleph proof, Alpha proof.
Alpha Proof.
So Alpha evolve,
Alpha.
Alpha.
So I think that Alpha Evolve is actually operating in a different setting. So they're trying like to prove some theorem, like the input is like natural language, and then they're evolving and trying to find solutions. But here it's kind of a different situation where you're provided with data, you don't know what the task really is, and you're trying to recover it from the data. But I might be wrong, so happy to talk about it later.
Although that also could be understood as a certain kind of device. If you put these two parts of AlphaEvolve together, because it has the deep learning part, but then it has this algorithmic part. And so if you put the two together, then that they add up to some kind of theoretical device, which is not like a deep neural net, but it's some kind of other, like you could characterize it in theoretical computer science, what that device is. And so, yeah, so then it could be studied like deep learning theoretic tools. That device can that particular device replicate it. So
Okay, yeah, happy to continue the conversation on that offline. Yeah, so that is kind of like the situation. Deep learning doesn't seem to work naively. We want to kind of come up with something else, but just to formalize it a little bit, we can actually prove that this framework of using stochastic gradient descent for training any model, basically like a transformer, an MLP, a convolutional network, whatever you want, will not be able to learn things like parity. Okay, so if we have a random parity function over this space, okay, so we have n dimensional vectors, binary vectors, and we have some k parity function, then stochastic gradient descent, doing coordinate optimization online requires at least this number of iterations, and as such also sampling. Okay, so we need n to the k samples and iterations in order to be able to learn the k parity function. Okay, so just, obviously we can plug some numbers. Let's say n is equal to 100 and k is equal to 20. Then we need like at the scale of 10 to the 40 samples and iterations in order to be able to learn the parity function. Okay, so SGD is able to learn that, but it needs to run basically forever in order to achieve some reasonable error. Okay.
Or why 10 to the 40, not 10 to the 20?
No, so it's like 100.
Yeah. Okay, thanks.
Okay, so that it is possible, but very hard. So the question is there an alternative method for let's say learning the parity function? Does anyone have an idea? I guess like the most basic algorithm that we ever learn, even before taking computer science classes. Okay, so Gaussian elimination. So we can basically put all of the samples as rows of a matrix and then do Gaussian elimination in F2. Okay, and then we can solve it with like O of n samples. Okay, and it takes us in the naive case n to the 3 compute. Okay, so
Linear.
yeah,
Your data is linear. Shouldn't be doing deep learning to
exactly. Yeah, you have a like a specific specialized algorithm for this task, and you can solve it, and it works great, right? So we reduced it from n to the k to n. That's awesome, right? But it's not the solution that we want, right? The reason why it's not good enough is because this is tailored for this specific problem, right? So now we know how to solve parity, but what about learning primality? What about learning palindromes, strings, manipulations, automatas, all of these, or graph problems? Like we cannot use Gaussian elimination on F2 to solve all of these problems, right? So that is basically the issue. So we want something more generic that is able to solve a broader space of learning problems. So there is an alternative method, also very old idea in machine learning that is kind of like alternative to SGD. So SGD is gradient-based search. We can also do just naive search, okay? So the alternative is to use something called empirical risk minimization. Okay, so what we do is we can think of the parity function as a Python code. Okay, so we can write it out as def fx returned XOR between x0 and x1 and x2, and that is an implementation of that function. Okay, and then we can do the most simple thing that one can think about, which is basically going over all of the Python functions in Python, okay, one by one, until we find the solution. Okay, so we can enumerate all of the functions that we can write in ASCII. Okay, so we have defFX0 and then defFX1 and so on until we arrive at a function that matches the training data. So we evaluate each one of them. Some of them may compile, some of them may not compile. Like these two do not compile, so we reject them. And eventually, sorry. Eventually, we land at a function that will match the training data. Okay, so that's an alternative approach. It doesn't have any gradient descent, no neural network, just that. And that actually is very sample efficient. Okay, so if the target function is a short program, then we can mathematically prove that we don't need many samples for this very basic idea to learn well with error epsilon. So in the 80s, people introduced that idea and basically proved the following theorem that says that if the target function can be written as, let's say, a Python code over the alphabet of ASCII, okay, so alphabet is sigma, then with high probability, this algorithm is going to output a function that has error at most epsilon if provided with this number of samples. Okay, so you can immediately see it's basically some O of M of L, O of L. Okay, so if the alphabet is ASCII, then we have 128 characters. So we have log of 128, and epsilon is, let's say, 0.01, and we have that as a factor, and then we have this L, okay? So the Python function that we tried to learn is actually very short, right? It's a few characters. So that is the length L, and then it means that we just need a few hundreds of thousands or thousands of samples in order to learn that problem. Okay, so much easier, and we can actually use that, revert it, and get the test accuracy as a function of the number of samples. Okay, just multiplying here by epsilon and dividing by m. And that gives us a lower bound on the test accuracy of the ERM algorithm. Okay? So that's the alternative method. And now we can basically go back to the plot that we had before and put the lower bound that I just introduced on the ERM performance in the plot as well. So this was the trained performance 100% of SGD, okay, with the transformer. This is the test performance of the SGD, it doesn't work. And this is a lower bound on the search-based algorithm, okay? That is going to be the minimum test accuracy of that algorithm. So now it works, right? Like, so we have an algorithm that works well, it's generic, it's great. But what is the problem with that algorithm? Anyone?
All right. So I see at least one thing that, so you restrict yourself to functions with low form overall. That's it. So you are comparing apples and oranges, because in the first scenario you have, like, you don't have any assumption on your function, and now you have the assumption that it comes from a low form overall complexity function.
Right, that is definitely one pitfall, that we assume that the target function is short, right? Like, because in my case, the complexity is the description length under Python with ASCII, but generally speaking, Kolmogorov. Yes.
Yes, so when you're not using the grammar of the language at all, okay, you're just enumerating ASCII values.
Right.
You basically have non-multiple.
Right, yeah. Basically, yeah, we're enumerating everything. We're not taking advantage of the data really. We're just doing naive search. And that is basically in my view, the main pitfall because it runs forever, right? Like even if L is 100, which is not so huge for programs, to run this thing, we need an exponential number of programs that we need to enumerate, right? It takes forever. So obviously, like we can calculate it, enumerating programs of length L over this alphabet is exponential in L, it's sigma to L, and then basically what it means is that it takes forever, right? So we had SGD that was fine, we were able to run it. Now we have an algorithm that is sample efficient, but it will never hot, right? We will never get the result that we want, even if it's sample efficient. And just to summarize this part, we can basically compare these two algorithms, okay? So what is the runtime of SGD? O of the number of samples. The sample complexity is n to the k, okay, for the parity function. Overall, we get n to the k runtime. And for the ERM algorithm, the runtime is this thing, right? Sigma 2L times m, the number of samples. If we plug the value of L for the parity function, so this is the length for implementing the parity function, we get n to the k. The sample complexity is k log n, okay? It's O of the length. And then again, we get an overall runtime that is n to the k, okay? So the sample complexity is much better, but the overall runtime is not great, okay? So that is the issue that we end up with. So this algorithm is interesting theoretically because it's working well with in terms of sample complexity, but it is not efficient at last, right? So this is what I want to do, and this is kind of like the contribution here in this work. So we realized that online SGD is sample inefficient, and ERM is runtime inefficient. Okay, can we implement ERM but efficient? Okay, that's basically the idea of what we're trying to do. And that's kind of like the idea of the solution. I guess it is something that people already raised. So this is like our data. This is the input data. We're going to try to feed it to an LLM, let's say GPT-5. Okay, and we want GPT-5 to write a program that will be able to classify the data. Okay, so that's basically the idea. And then if it works, then it inherits the sample efficiency of ERM. Okay, so it will be very sample efficient. And at the same time, because like this LLM is going to run for like a pretty short amount of time, it will also be runtime efficient. Okay, and the idea is super simple. Basically, we do something very simple, very similar to AlphaEvolve. We generate a pool of candidate programs using a reasoning augmented LLM. Okay, we verify each candidate on the train and validation sets. Okay, so we split the training data into train and validation, and we evaluate on that. And then we just pick the one that best fits the validation error, okay? That the validation error is smallest. And that's how we get both good runtime and also sample efficiency. This is kind of like an illustration of the algorithm. Super simple. So we have the training set. We build a prompt using the training set. Okay. Then we give it to the LLM. And then we basically run it k times until we get that the validation error is smaller than a certain threshold that we fix, or that we attempted too many times and then we stop. and then we pick the best solution so far. Okay, that's the algorithm. And this is kind of like a simplified version of the prompt that we use. We say something like, given sequences and labels, output a single Python function that implements the underlying rule. Okay, so we give it the training data here, like sequentially, and we task it with outputting Python code that will match the training data.
So the prompt is 100,000 data points long or something. Big prompt.
If the data set is so big, yes. But we wanted to design an algorithm that is sample efficient. So the argument that we're making is actually you can just put a few hundred samples and you'll be fine. Yeah.
In other words, the context window.
Yeah.
Data sets that are much bigger for the context.
Right. Yeah. So it can only work under like today's LLMs and scale if it's really sample efficient as we claim it to be. Yeah. So yeah, so we tried many different tasks, and for each one we have kind of like a challenge behind it. So we have the parity function. Okay, so let's say we have 100 bits and we look at 10 parities, or like 3 parities, whatever. So we have 100 choose 10 different 10 parities over 100. This is at the scale of 10 to the 13. We cannot just enumerate all of them. We need the LLM to be able to come up with a solution fast. So it needs to kind of like have ran like some good internal algorithm in order to solve this. Is palindrome. So basically classifying 2 sets where one is of palindromic sequences and non-palindromic. And we made the negatives hard by basically generating them as palindromes with 1 bit flipped. Okay, so we want to classify these 2 things. We have pattern matching. So we have a given sequence and we want to say a given predefined sequence is a subsequence of the input. Okay, so it's kind of like finding a needle in a haystack. And then we have DAIG2 language that we convert into binary. And again, the negatives are basically DAIG2 language with 1 bit flipped. So it's wrong only very locally. And we have is prime. Basically, I mean, it's hard because primes are kind of like pseudo-random. You guys probably know better than me. And like if we have 100-digit primes and non-primes, like we have about 10 to the 97 different prime numbers of that scale. So like the LLM cannot remember all of them. So if we give like, let's say 200 samples of primes, it cannot just be like, oh, these are primes. I know these primes from my memory, because it doesn't have the capacity to hold all of these numbers. Okay, so it really needs to figure out that there is something here, and not just like recall, oh, these are primes and spit out the primality function. And we have cellular automata. So we took some cellular automata and then we took the parity of that. And the SHA-256 parity. So basically calculating the parity of the SHA encoding of the input. Okay, so these are the functions. Each one of them is difficult in its own way. How many of these do you think that our algorithm was able to solve?
It's not all, but you sure the best.
So not all of them, yeah. So basically all of them except, what's that?
All but SHA.
All but SHA, yeah.
I
So
was gonna say, if you can solve SHA, then
then
forget everything else.
yeah, I'll just write a paper on that, right?
Big question.
So the reason why we actually investigated SHA, and I think SHA is a very interesting example, is because the naive ERM implementation is able to learn SHA. Like the algorithm that I detailed with the naive search, just going code by code in ASCII, will be able to learn it with a guarantee. And our algorithm, our implementation of the ERM algorithm is not able to learn SHA, but it is able to learn all of the latter functions. Okay, so let's look at some, oh yeah.
So maybe to go back down. Wait. I think two sides.
Okay, this one, or
Or maybe one more.
you tell me?
You say something that all negatives are palindromes with one bit split.
Yeah.
And you say this is why it's chunk. Is there really something that makes it one palindrome?
Yeah, of course. So let's say you,
Completely palindromic.
it's, it's much more difficult to distinguish between sequences of palindromes and random sequences compared to like palindromes and something that looks almost like a palindrome, right?
Give a human 100 digits and
No, but
say, is it a
it's
palindrome?
visible evidence. Say if I get, so there could be unless random structure hidden in palindrome of random. But sort of your positives and your negatives have a lot of stuff.
That's why it's
So
hard.
sort of, well, that's why I would say you need to come up with a hypothesis. Because I can always verify, okay, this is a palindrome, this is a almost palindrome.
Maybe,
So my question is more or less just if you tested it or not.
yeah, it did work
Is there a
even,
chain of reasoning for this?
yeah.
Does it realize what's going on?
Yeah, so not for palindrome, like I didn't put it here, but we have some chain of reasoning to start with for other tasks. So this is primality. So we had two versions of primality, by the way. One is just like primes and non-primes, and the other one is primes and non-primes that end only in 1, 3, 7, and 9. Okay, so like it's not easy to, like it's like even or ends with 5, all of the trivial cases. So we wanted to avoid those. This is the trace for, I think, regular primality. So this is kind of what happens. And I think these traces are pretty interesting. So it starts by like saying, okay, maybe the function that is hidden here is like majority of odd digits. Okay, then it got accuracy 51%. Okay, bad guess. And then last digit is odd. Okay, then we're able to get rid of all of the evens, right? And then what about divisible by 3?
Sorry, only 77% of the primes have odd last digit?
No, like the classification error. So basically, like you basically cut half of the non-primes, right? So you got like
Classification error.
Cla-
So it's guessing that, it's guessing, okay, what if the answer is last digit is odd,
yeah,
and then it gets 77% accurate?
yeah, like you compare that function with the ground truth function, which is primality. Yeah, so it's 77 because we have a small data set, it's like 200 samples. And then it is okay. Maybe I should add like divisible by 3, using this version of that. Then exclude last digit 5, and then adding more and more primes. And here it's interesting. It is kind of like, what if I take 7, 11, 13, and 43? I guess it just tried to play a game with it and see if there is some pattern or if it's robust. And then the hypothesis was positives are prime numbers. And then it returned the function that is Miller-Rabin test, and that was the final solution. Yes.
Yeah, so the examples you presented on the previous slide as where you get shots of 56 tonality, etc. Those all seem like popular tasks. So I'm wondering like what happens to your write a random program, generate your test, and then try to learn that random program. So if you try anything that's not a popular program that it might have been trained on, etc.
Yeah, so I think it's a great question, and we should definitely do more of it. So I guess like now that I present it as a talk, it all looks clean and easy, but this thing was not easy to do. Like we tried many different LLMs, and also Gemini didn't work with that. Like only GPT-5 was able to do that. So I think that is already like a step that we wanted to achieve. But I think some of these functions are not obvious, like the cellular automata parity just came up with this arbitrary rule for update, and then we took the parity function over that. So you have a composition that is not something that we typically do in coding. Primality, I agree, but that function is like a bit weird. But one thing that we want to test is like, let's say, prime plus 5 or things like that. Yeah.
Given chart was like should be a Python library function, right?
For sure.
Yeah. So,
Yeah.
still it's not able to learn that.
Right, because it's so like pseudo random that you're like, I mean, even if let's say you introduce some other pseudo random function, then the error is going to be 50%, right? Like it will always not do well, so you don't have any signal to go with. Yeah. This was, in my opinion, a bit more interesting. This is for the parity function. So we have 10 parity. What the LLM is doing here, it is basically trying to look at like some basic functions to check for correlations. Okay, so it compares it looks at the correlation between like one's count threshold in some set of values and see if it is correlated with the labels. It's not correlated, and then it tries parity of ones, like parity of everything, and then the edge bits, like are these correlated with my function? Also no. Okay, so it was like, okay, so it's not correlated with this function and not correlated with the full parity and not with the first input and not with the last input. Then I suspect that it's probably a parity function, because if you take any two parity functions, even if they are distinguishable only by one variable, then the error between them is just 50%. Okay. So what it says is, okay, this is probably a parity function. I run Gaussian elimination over F2, and then I recover the support. So this is exactly the support that we had. And that was the final hypothesis. Yeah.
Yeah, just to add to this, a really nice point is that I think the phase switch is happening when the LLM realizes, oh, this is probably what the function is. And then it sort of tries to build the right test and gets it. So if you put in a function that is not well known, it's possible that it's much worse. Do you think that's possible?
I don't know. So I think it's worth looking at, and I think like the space of known things for LLMs is much more vast than we imagine.
Sure.
Like they have seen basically everything, and we don't have a concept of the whole internet. So I don't know like exactly what are like those edge cases, but yeah, it's definitely interesting to explore.
The idea that was brought up over there, you generate a random program that generates a certain list, and you want to see if your construction can reproduce that program.
Right, or like a circuit, random circuit, yeah.
And then it won't have seen it before if it's
Yeah.
Or something like the function prime squared plus prime plus 1. For example, if you just ask it to say, like generate a function that can list b squared plus b plus 1, like then it might.
Right, some like polynomial over the primes and non-primes, yeah, definitely.
do it on base 7.
Yeah.
Right. Yeah, I'm wondering, like, if you try running, what would like this tree look like? You just actually just gave it random numbers. Like,
What do you mean by random numbers?
Like you just generate random numbers and you try like something. Oh, learn the kind.
Oh, like
from actual random number gen.
random labels?
Yeah, random labels. And like, I assume it probably wouldn't find some weird.
So one thing it could do, for example, and I don't know if that will happen, but it's worth checking, is basically write a table, right? Like if this is the input and this is the output and so on, it will be a quite longish program, but it's possible to do that. That's overfitting, right? It will either overfit or will just say I cannot find a solution. Yeah. Yeah, so going back to the experiment that we had before with the random 10 parity, now we can also compare to LLM ERM. So So SGD was trained with 100K samples. As before, it fails. LLM ERM achieves 100% at test time. Okay, so completely succeeds. Then we also have here the cellular automata parity and is prime, where the numbers end by these values. And this is for the question about different LLM architectures, like at different scales and so on. So we tried like lots of architectures on these tasks. So we have Qwen 3, DeepSeek Coder, Llama 3.2, 1 billion, whatever. And basically across all of these tasks, so we had many of them, they fail if the input dimension is too high. Okay, so here the parity function completely doesn't work. Here for pattern matching, it stops working around like this area. So that's nice. Okay, so we know that training from scratch with SGD provably doesn't work on some kind of these problems. And also empirically, we see that it doesn't work. But in some sense, one could say, oh, this is not fair, right? Your LLM ERM is based on this pre-trained model that was trained on the whole internet, and you're training from scratch models, even if with more samples, with 100K samples, but they don't have the pre-training that you're providing your algorithm. Okay, so we tried to see if there are stronger baselines that we can compare to. So one idea is to use fine-tuning. So we take a pre-trained LLM and we try to fine-tune it on the data that we have at hand. Another thing is to use in-context learning with instruct models. And another idea is to use in-context learning with thinking models. Okay, so thinking models are these algorithms that do this internal thinking on a scratch pad. And instruct models are those that are trained step by step against the verifier. Okay, so both of them are trained for things like theorem proving and so on. And we wanted to see, so in-context learning is basically giving a prompt to the model with the data and telling it to adapt to the data. So we want the model to switch context and behave like the solution instead of what we do, which is spitting out a function that solves the problem. Okay. So that also doesn't seem to work very well. So this is fine-tuning. So we did fine-tuning over the whole model, only top 2 layers, 4 layers, 8 layers. We tried many different configurations of hyperparameters for the fine-tuning. Basically, nothing really worked. The models are consistently able to fit the training data, but they fail to generalize almost completely. And this is the prompt that we used for the in-context. So we give the data and we give a new sample and we want it to predict the label. Yeah.
So here, I think the previous slide was overfitting into the training data, right?
Right.
What if a smaller model is used?
What's that?
A smaller model is used with less parameters.
A smaller model?
So the idea should be that not to overfit too much to the training data, right? Assuming the distribution is same for the train and the test. So here, yeah, it looks like it's overfitting to the training data. So it's just basically learning everything, including the noise. So yeah, it wouldn't fit on the, like, yeah, it will not be able to come up with a good test score. So although you have mentioned that, I think you fine-tune for your layers and stuff, right?
Yeah, so that was the answer I wanted to give you. We, let's say, fine-tune the top 2 layers. So that is a much smaller model, right? We use pre-trained model which was trained on the whole internet, that was trained with, you know, the most frontier ideas in LLMs, right? Instructing and thinking, RL and everything. And even though it still doesn't work very well. Yeah. So Next, we looked at in-context learning. So this was a simplified version of our prompt. Basically, we give the model the data, part of the prompt, and then the near sample that we want to predict, and we want it to predict a little bit based on the context. Okay, so this is kind of like the results we got. So these are results with DeepSeek Coder, which is an instruct-tuned model. We have approximately 50% accuracy on all of the tasks. Okay, so here each one of these curves is a different task that we evaluated, and we see that, yeah, like nothing gives a signal that there is some way to succeed here. And this is for thinking models. So we have Qwen3, and we looked at these tasks. And interestingly, it kind of works better in the primality task, which is interesting, but also not as close as to like the idea of LLM here. And another thing that we tried to understand is to what extent our model, our method is able to do length generalization. Okay, so let's say we trained the code that we generate based on vectors of length 10. Do we generate code that also generalizes to other length? Okay, so we kind of see that it happens consistently. So the train accuracy is always for these methods 100%. We train on 10 dimensions, and we can see that it does well on 10 dimensions, but also generalizes to up to 100 dimensions. Also for pattern matching, and for each palindrome, we have kind of a decay. So it wasn't perfect. Yeah, so just to summarize, basically, I think it kind of like, there are all of these questions about expanding these experiments and so on, but I think this might be an interesting new paradigm to think about. So for ages, we kind of preached that back in VC bounds, like the ones I introduced for why ERM is actually good. So they were ridiculed. People said, oh, VC dimension is too big and so on. But actually for learning small, short codes, VC dimension is actually very favorable. It was this O of L, right? And the problem with pack learning in this case actually is the runtime. So we're introducing some kind of a remedy for the runtime, but it is interesting to understand, like, where can we take it? Like, to what extent this can be actually practical. So I believe the bottleneck is actually the search, and that's what we're trying to do here. And I think it also introduces some interesting questions from a scientific standpoint and also application standpoint. So one question that people ask is what kinds of data, right? Like if we can make the problem more and more complex, will it still work, right? And maybe we can do solve questions in bioinformatics with that, with Tableau data, or maybe even images. We can put the images as encoded within the prompt and so on. What kind of architectures? So some kind of an interesting question that we kind of got some intuition around is that most models that we currently have don't work very well with this system. They're not able to do this learning. So what are the components that we need? Do we need recurrence? Do we need tool use? Do we need memory? It seems that GPT-5 is basically the only frontier model that is able to do this thing. But what is special about it that other models don't have? Another question is, basically we introduce some setting where we can study new properties of success. Okay, so we have the test time accuracy. So learning has always been about improving the test time performance. But now we can also ask questions about runtime and memory usage, right? If we spit out the code, then we can ask like how fast the code is, how memory efficient the code is. And I think it kind of resembles what actually happens in human learning. If we think of like a kid that is learning to do math, we evaluate them on their performance to accomplish and like to solve problems, but we also care about how fast they do it, right? And that is another dimension of learning that we completely ignore in machine learning. And I think that is a very valuable question, as not just from a scientific standpoint, but also an application. So, for example, in complexity theory, people kind of speculated for a long time what is like an average case. So in my view, an average case is, let's say I have a distribution of tasks, let's say a distribution of graphs or numbers, and we have some property that we're trying to solve, okay? So what is like an algorithm that does well on this distribution specifically? And I think that within this framework, we might be able to tackle that. So you have samples of graphs, maybe easy graphs for TSP, and then we want to use LLM to come up with an algorithm that works well for this specific set of graphs. And I'm very curious to explore that. So distribution-aware program learning. Another question is automatic data scientist. So can we use this thing for tabular data, where LLM explores different ideas and pre-processing of the data and so on? Yeah, and obviously, as mentioned, expanding it to more and more tasks. Thank you very much.
Any questions? It's time to speak again.